These rocks have been here for millions of years, and they'll probably be here for another million years at least. This piece of glass was probably made a few months ago, and it's not here much longer. But these same thing. Sand. Granite, glass, sand, the shell on this egg, the bones in this chicken. They all belong to the same class of materials, ceramics. And most people think of ceramics as the stuff you make plates or cups out of. But the properties and benefits of ceramics now go way beyond such mundane items. In fact, almost since time began, ceramics have been the most durable of materials, and today they could play a major role in making your products world beaters and in cutting production costs. Making packaging such as these cans is a very demanding business. Each can has to be made to very high standards of dimensional tolerances and surface finish, and at very high line speeds, 2,000 per minute in fact. The tools which punch out the cans take a tremendous battering. When this happens, the machines have to be stopped and the tools replaced, so valuable production time is lost. These metal tools have lasted about 2 months. However, these ceramic tools, developed by MB Group Technology, have lasted for 20 months and still show no signs of wear or damage. This means an extra 4.5 million cans per year, and what's more, the cans are of a higher quality. Ceramics are also important to farmers. This metal seed drill is badly worn and has to be replaced. However, this ceramic drill not only lasts much longer, it plants the seeds more accurately and thereby increases the crop yield. Although the drills are initially more expensive than metal ones, in operation, ceramic drills save money. The farmer doesn't have to keep stopping to replace them so often, and he doesn't need to buy so many spares. And ceramics are vital to the efficiency and cost effectiveness of many other products. Stonehenge is a classic example of the durability of nature's ceramics. But if you want to make the most durable structures out of nature's ceramics, you build arches, as the Romans did 2,000 years ago. These ceramic materials have resisted attack from the elements, partly because of what they're made of, and partly because of how they're put together. Granite mainly consists of oxides of silicon and aluminium, which do not rust, which is more than can be said for some man-made materials. Of course, this ceramic doesn't rust either. But just a moment, if this and this are made of the same material, how come this is so durable and this is so fragile? Well, it all depends on how they are made. Granite is made under conditions of great heat and pressure. And the pressure is so immense that the crystals are squeezed very tightly and closely together, so that almost all the gaps that would form faults or planes of weakness are squeezed out. I say almost all, not all of them, because if all of them were squeezed out, then we would find today that granite would be much more difficult to shape into building blocks. The hardest of all materials, diamond. The reason is that the is like this. This is actually a very difficult structure to make, and like making granite, it requires heat and very great pressure. Although the bonds between individual atoms in a diamond are very, very strong, it still contains planes of weakness in certain directions. This enables skilled craftsmen to fashion a rough diamond into a beautifully faceted one, like this. Flint is another ceramic. Its flaws and planes of weakness in the structure became very useful to our ancestors. They found they could fashion it to make useful shapes. By taking a flint and striking it with another flint, they could get it to fracture along its faults. Jade has a very different structure from flint. Flint is really a sort of glass, whereas jade is made up of lots of needle-like crystals, all tangled up together and packed very tightly. This means you cannot chip bits off. The people who made this ceremonial axe head had to grind it into shape using sand and a piece of wood. This would have taken months and months. Jade is tough, whereas flint is brittle. But here's a question. Why can't we make ceramic components for industry as tough or tougher than nature's toughest and best ceramics, but still at a price that industry can afford? Well, we can. But first of all, let's try to understand exactly what we mean by tough as opposed to brittle. The problem is, for a long, long time, people have been confusing toughness and hardness. Pliny the Elder, in the 1st century AD, gave us a test for identifying a real diamond. He said the diamond should be placed on an anvil and struck with a hammer as hard as possible. If it breaks, he said, it's not a real diamond. Didn't think I was going to do it, did you? Either Pliny had a ready market in broken diamonds, or he'd really confused hardness with toughness. Piece of glass. If I hit it with the hammer, it disintegrates. If I hit the diamond with the hammer, it would have broken into lots of little diamonds, because although it's hard, diamond is brittle. Now, metal is tough. It's tough because it can absorb the energy from these hammer blows. Ceramic is hard, but it's brittle, because although it can absorb the energy of the blow, in doing so, it disintegrates. In fact, we make use of this shattering of ceramics under impact in this lightweight body armour. Ceramic tiles, first of all, blunt the bullet. The bullet breaks the tiles into lots of tiny fragments. It's this breaking into tiny fragments that absorbs much of the impact energy. If metal were to be used, it would bend and transmit the shock wave into the body, and this shock wave would be more lethal than the bullet. But if ceramics can't absorb impact energy, what happens if you apply the energy gently? Well, as far as glass is concerned, it doesn't matter whether the energy comes from a bullet or a strain energy from someone leaning on it. Eventually, if the same amount of energy is applied, the glass will break. Of course, we all know that if we want to break a piece of glass in a controlled fashion, we use a glass cutter. Now, why does it take so much less energy to break the glass after we have scratched it? The scratch has reduced the thickness of the glass by a small amount, but what is more significant is the concentration of stress around the scratch. The scratch is, in fact, a stress razor. Stress razors come in various forms: a sharp corner, a step, as well as a surface crack. And of course, flaws inside the material can act as stress razors. And now we can begin to explain why some of our man-made ceramics are not as tough as nature's. Although this potter is applying pressure and extruding the clay to mix it and squeeze out the air, the pressure is nothing like that exerted when nature turns clay into rock. But if we happen to break a pot, and look at the edges of a piece under a microscope, what we see is lots of flaws, which are pores caused because when it was made, all the air wasn't squeezed out. Now, if we wanted to make an industrial ceramic, we wouldn't start with clay, which is full of impurities. We'd start with powder, and the powder would be mixed with a binder and a sintering agent, possibly, and then pressed and heated till the particles fuse together. This is known as sintering. Now, because the particles are all different sizes, in the material you always get holes or flaws, and this occurs in all conventional industrial ceramics, even cement and concrete. And the result is the material is inherently weak and unable to withstand strain energy. Now, this spring is made of metal and was built to withstand strain energy. So if you had a new ceramic and you wanted to test how good it was, it might be a good idea to make a spring out of it. But could you do that? Well, this is a spring that can withstand strain energy, and it's made from cement. How? Well, let's ask the man who made it, Professor Derek Birchall. Derek.
Thank you. Well, this spring and the other material that broke so easily are the same material. And the difference is that in this material we've taken the defects in it, whereas in that material, as you said, it's filled with defects. And if we look down a microscope at that material that broke so easily, this is the sort of picture we get. That's 1 millimetre. And what you can see these holes are voids, probably caused by air bubbles or gas bubbles. And that void there is nearly a millimetre long. And that's responsible for the easy fracture of that material. By changing the process by which this material is made, altering the process completely, we can make material like this. Looking down the microscope at this spring material, again we have a 1 millimetre bar here, and you can see that unlike the other picture, there are very few or no flaws present. And even if we blow up this little area here and magnify it still further to this picture, you can see still almost no flaws. What there are very small.
So the fewer the flaws, the stronger the material.
Indeed, and that was discovered by Mr. Griffiths in 1920. So let's take a look at his equation. This is the Griffiths relationship. It says that the strength of the material is dependent on 3 important properties of a material. The first, E, is the stiffness, how stiff the material is. And the second property is how much energy is needed to break it, the energy of fracture. And the third most important property is the size of the sort of flaws we've been looking at. The size of them is C. Since C divides into these 2 top numbers, the smaller this is, the bigger is the strength. So one of the ways of increasing strength is to reduce flaw size.
But how do you go about doing that?
Well, C is reduced by, first of all, having powders which are small in size, uniform in size, and very pure, and they contain no impurities at all, no bits and pieces. And then you have to pack those particles perfectly together, leaving no air bubbles in, no mistakes in packing. And this electron micrograph shows us the microstructure of a very strong ceramic. You can see the particles are small, they're packed together, there are no mistakes in packing, no air bubbles. This is what happens if you get an impurity in the mix. This is obviously a great hunk of some impurity that's dropped into the mixture, and you can see it's disrupted the structure. There's a big hole round it because it's not sintered, and that is a Griffith flaw. That would make the material weak. It's a question of perfection.
Right.
So next we need the right sort of organic binder, which sticks these things together before they're sintered in what's called the green state. And we want that binder to disappear smoothly when the body is put in the furnace, so that it doesn't disrupt the structure. Then we've got to mix the system up, the liquid, the carrier, which may be water, the organic binder and the powder, mix them up vigorously to form a sort of plastic mix so that all the particles pack together perfectly. This gives us what's called a green body or a green state. And the way the new technology is being developed is that the green state is much stronger and tougher than has been the case in the past, so that the green state doesn't get damaged easily. It can be machined accurately because it is tough. So because of the uniform packing, and close packing, the shrinkage is very uniform and small.
Right. So you've got a much better ceramic, but where does this lead us?
It leads us to making ceramics that are very strong. For instance, this is a spring made out of aluminium oxide, and as you can see, it is quite strong and very flexible. It's about twice as strong as has so far been attained with aluminium oxide. And we've been able to use the same technology to make a coil from the new superconducting ceramics. This is the first time such a thing's been accomplished with these new materials.
So now we can make ceramics that are as strong, as tough as metals and plastics.
We can make ceramics that are strong, and we've removed one of the things the engineer doesn't like about ceramics, the variability. The toughness is increasing, but it's another problem.
So what is it that makes metals so tough?
It's their ability to plastically deform that makes them tough. If you crash your car, straightening out all the crumpled bits and the bent bits may be quite expensive, but all the energy has gone into buttling and bending metal and deforming it plastically rather than into your body. It's the nature of the bonding between atoms in a ceramic that makes them hard and strong, but it also stops them from plastically deforming, so that the cracks in them open up under tension. Held under compression, the cracks can't open. That's why ceramics are strong in compression and why those Roman arches are still there.
So what methods have we developed to make ceramics tough?
Well, one method is to put fibres in the ceramic to make a fibre-reinforced ceramic composite, as has been done in this component from a paint stripper.
These heat insulation shrouds for the Black & Decker paint stripper are made from an inexpensive slurry of short ceramic fibres bonded together with starch. This ceramic composite is fitted into its metal casing and then dried. The ceramic insulation shroud will be heated up and cooled down repeatedly and will also have to stand up to accidental impacts. This means it has to be tough. Brittle materials find it hard to stop a crack. Cracks start from a surface defect and run through the material. But when fibres are incorporated, the interfaces between the fibres and the surrounding material open up and blunt the crack. Because ceramics are good thermal insulators, this paint stripper can be operated at a higher temperature. This means that the paint is stripped off more easily, without the paint stripper handle becoming hot or its plastic casing degrading.
Another method of toughening is called transformation toughening. This is a transformation toughened ceramic. In it are little grains which, when the crack tries to pass them, transform, and you can see how tough it's made it. It's flexible.
Wow.
There's another domestic application. What sort of cooker hob have you got?
Oh, we got a glass one.
A glass ceramic one.
Right.
And that is heat treated so that little crystals grow inside it. And the crack has to propagate round these crystals, which makes it unlikely that it will crack. And also, it will withstand extreme changes of temperature.
Now, your mentioning kitchens has made me feel hungry. Come on, let's go and eat. Thank you.
Thank you. Thank you.
Oh, these are delicious, aren't they?
Well, they are indeed.
But this, I mean, mussels. This is a ceramic, isn't it?
It's a ceramic, a natural ceramic. It's a natural ceramic composite because the creature inside had to develop protection against predators who want to eat it, as we are, and against the action of waves, salt water, being bashed against rocks, and so on. So it had to develop a tough and strong ceramic, and it's tough because it's a composite. And if you look down a microscope at it, it consists of little thin plates, all stacked up together and glued together by protein. And so you can imagine how difficult it is for a crack to pass through that.
And what's it made of?
It's calcium carbonate, about 98% chalk.
Really?
And this stuff is 10 times stronger than conventional cement.
Ah, but your cement is much stronger than conventional cement as well.
Indeed, it's about as strong as this shell.
Wow.
And it, again, is a composite.
That's amazing. So what else is on the ceramics menu?
There are many new things. For instance, here's a ceramic knife. And the advantage of this is it's very sharp, and because ceramics are very hard, it keeps that very sharp surface. And also because it's inert, it isn't corroded by the juices in food like fish, and it doesn't get tainted.
So it should last a long time.
So it should last a very long time without resharpening.
We could do with a joint to carve, couldn't we?
We could indeed.
Well, I have here a joint, and this is a hip joint with a ceramic bearing.
A ceramic bearing. It's new, and its advantage again is that that ceramic bearing is hard, so it doesn't wear. It's strong, and it's inert, so it's not attacked by the chemicals in the body. And here's another bearing made of a ceramic. Ceramic balls and ceramic bearing surface. And the advantage here is the ceramic is much lighter than a metal. It's very hard, so that it doesn't need lubrication. The friction between a ceramic and another ceramic is very low. No lubrication.
Even at high temperature?
Even at high temperature, where metals get sticky because they melt.
Well, I don't think I could go very long without lubrication.
Here's to ceramics.
Here's to ceramics.